Welcome back, everybody. In this video we're going to be talking about perfect square trinomials. Now, perfect square trinomial has this format: a squared plus 2ab plus b squared. There's another form of a perfect square trinomial: a squared minus 2ab plus b squared. So to identify a couple goals here with perfect square trinomials, we want to be able to identify them, but we also want to be able to factor them. Identifying them, you first look for a perfect square at the beginning and at the end. You take the square roots of both of those items, the first term and the last term, and you know it's a perfect square trinomial if the middle term is 2 times whatever a is times whatever b is. It also works for this one down here if you have a minus 2ab. Now, the thing about perfect square trinomials is they're easy to factor. If they have this format, they factor into a plus b times a plus b. Once you figure out what the a term is and what the b term is, you know it has this format. This can be simplified further by just writing it as a plus b quantity squared. Same thing down here: a minus b times itself, and then you can abbreviate that by saying a minus b quantity squared. All right, so our first exercise here, let's just work on finding the perfect square trinomials. Remember, we're trying to look for perfect squares at the beginning and the end. So yeah, x squared is a perfect square. So right away that makes all 4 of these candidates for perfect square trinomials. Look at the last terms. We have a 16 here, that's a perfect square. 49 is a perfect square. 75 is not a perfect square, but 169 is. So we can mark out C. It's not going to be a perfect square trinomial. Now, what we need to do next is take the square root of everything, the first and last terms here, and that'll determine that quote a and b terms that we were talking about. The square root of x squared is x. That happens here. We won't worry about c. And then we also take the square roots of our perfect squares on the other 3 here. The square root of 16 is 4. The square root of 49 is 7. The square root of 169 is 13. See, so now we have our a and b terms. Now remember, let me write that formula up here again: a squared plus 2ab plus b squared. So we know that the first and last terms are perfect squares. We got to check this middle term for each of these. We want to see if the 4x, 14x, and 26x match that 2ab. All right, well, 2ab for each of those. On the a, it's 2 times x times 4, and notice that gives us an 8x. 8x should be the middle term. It is not. It's a 4x. So a is not a perfect square trinomial. It almost is. It almost is, but not quite. Let's check b. 2 times the x times the 7, 14x. And notice that matches the middle term. B is a perfect square trinomial. We know C isn't. Let's check D. 2 times x times 13. 2 times x times 13 equals 26x. It matches the middle term, doesn't it? So in this set, B and D are in fact perfect square trinomials. X squared plus 14x plus 49, x squared plus 26x plus 169. All right, now that we've identified perfect square trinomials, let's try to factor them using that formula. Remember our formula again: a squared, in this case minus 2ab plus b squared. And if it has this form, which we know it does, this will factor into a minus b times itself, which I'll write as a minus b squared. But in this problem, notice the a term is a p and the b term is a 16. All right, we're going to take the square root of each of those. The square root of p squared is just p. The square root of 16 is just 4. Those two terms go into our format here of the factored form of this equation. We're just going to write p minus 4. Let me demonstrate real quick why that works and why that factors. P minus 4 quantity squared. Let's take it times itself. The FOIL method, first, outer, inner, last. If we have p times p, notice we'll get p squared. If we have p times negative 4, we'll have negative 4p. If we have negative 4 times p, negative 4p. And then finally, negative 4 times negative 4 gives us the 16. Notice our middle terms here, negative 4p, they're going to combine to make negative 8p. As we can see, this is why the formula works. Our p squared minus 8p plus 16 is our original problem. And I just proved to you why the factoring works. P minus 4 times itself does equal the original quadratic here. But to factor, here is the correct factored form, just to go over the final answer again. Alright, let's look at another one here. Factor completely 25g squared plus 60g plus 36. Alright, looks like this has this format. We know it's a perfect square trinomial. This is going to factor into a plus b quantity squared. A plus b quantity squared. It's just a matter of figuring out what the a and b term are. If we take the square root of the first and last term, we'll have it. The square root of 25g squared is 5g. The square root of 36 is 6. So now we can get an answer to this in the format a plus b. In this case, our a is 5g and our b is 6 quantity squared. That is the factored form. Now let's talk about something called the difference of squares. The difference of squares is two square terms being subtracted. That's simple. That's all it is. That's why we call it the difference of squares. Looks like this: a squared minus b squared. And it will always factor into this. We can say a plus b times a minus b. And if you want to write the minus term first, that's fine. It's the same result. A minus b, a plus b. Either way is the factored form. It's just a matter of figuring out what the a and the b are. To do that, we just take the square root of each one. First, let's get a little practice just identifying a perfect square trinomial or a difference of squares. Let's see, h squared plus 1, that's a sum. T squared minus 20, it's a difference, but 20 is not a perfect square number, so b is not going to work. However, c and d work. Those are the difference of squares. X squared minus 4, 4 is a perfect square. A squared minus 169, 169 is a perfect square. Now, even though the problem's not asking for a little practice here with factoring, we can factor c, something plus, something minus. We can factor d. I'll write that one as the minus first and then the plus. And to find these, all we need to do is take the square root of each thing. The square root of x squared is x. The square root of 4 is 2. So this factors into x plus 2, x minus 2. Down here, the square root of a squared is a. And the square root of 169 is 13. So there's a little practice with that. Now, if we were to multiply these out right here and use that FOIL method, it would equal the original problem here. Alright, so you could try that on your own to see if it works. But these are the factored forms. Even though the problem didn't ask for it, we were just asking for identifying C and D. And then let's see about factoring completely here. Alright, remember the formula. Remember the a squared minus b squared. Something is squared minus something is squared. That is in fact the difference of squares. It'll factor into something plus, something minus, doesn't matter what order. Something plus minus the something, something plus the other something. To find that out, all we need to do is take the square root. The square root of 25q100 is 5q to the 50th power. To find the square root of an even exponent, you just divide the exponent in half, divide it by 2. Square root of 121g to the 16th, 11g to the 8th. 11g to the 8th. So those are our two terms. That's our a term. Think of that as the a term. Think of this as the b term. All right, and so the one that seems to match, looking down here at C, B, definitely A and B don't work. They don't have the plus and minus terms. C doesn't work because the exponents are wrong. D is our winner. Notice the exponents, 5q to the 50th. The plus over here, 5q to the 50th plus, 5q to the 50th minus, and notice the 11g to the 8th matches. There we go. All right, thank you for watching. I hope this helped.